I've recently been working with the Weaviate team on vector search engines. One of our projects that I'm the most excited about is creating web demos where anyone across the world can see the power of neural search for themselves, for free. I'm really excited to share that there are two new web demos in Weaviate, both of which are linked in the description of this YouTube video. These datasets are Wikidata and Wikipedia. This video will explain all sorts of things around this, such as the difference between Wikidata and Wikipedia, how graph embeddings are computed with Facebook AI's PyTorch BigGraph, a visualization of the demo itself, and a conclusion where I present my ideas on how I'm using graph structured data and how I'm currently thinking about the field of graph neural networks in deep learning and knowledge graphs. Thank you so much for watching. I really hope you enjoy this presentation, and I'd be more than happy to answer any questions you might have about these ideas. As mentioned previously, this is explaining the demo of the Wikidata dataset for vector search engines implemented with Weaviate. Before getting into the details of Wikidata, it's important to know the differences between Wikipedia and Wikidata. In Wikipedia, text is organized as it's most natural in human civilization, as we read articles, read papers, or all sorts of things from tweets to text messages, how we naturally organize language from left to right using a composition of natural language tokens or words that make up this kind of expression for communicating information. Wikidata is less natural but more information dense. It's where we explicitly represent nodes and other nodes based on some kind of edge, relation, or property that describes how these nodes might be linked together. So for example, Miami Heat is an instance of NBA team. We have a very information-dense style of representing information that we hope to integrate with these deep learning architectures and all sorts of data science and artificial intelligence applications. So more concretely, as we're looking to use gradient descent, backpropagation, and deep learning algorithms with these kinds of data types, in Wikipedia we represent this information as discrete word tokens. A naive strategy, the bag of words approach, would be to have a separate discrete token for each unique word that appears in the vocabulary. So for example, as we have this, the Miami Heat are an American professional basketball team, we'd have each individual words maps to an individual discrete token. But more commonly, we break up these words into subwords to make up these token mappings. So we have these discrete numbers that represent positions in an index table, and then from each of these indices, we index a continuous vector embedding representation. So heat and R and an all map to some dimensionality of input vector, maybe 512 dimensional vectors for each of these discrete word tokens. Compared to Wikidata, where we use adjacency matrices to represent this information. So an adjacency matrix is an n by n matrix where you have on going left to right the nodes in the network, and then from top down you also have the nodes in the network. A 0 indicates there's no edge between the nodes, and then you have different kinds of edge signaling to denote having more than one kind of edge. So as we'll see, Wikidata has greater than 5,000 different kinds of edges, so we need more than just binary adjacency matrices to encode all these different kinds of edges. But similarly to word tokens, we're going to be mapping these edges to continuous vector representations as well. So the edge signal 8, the discrete signal of a different kind of edge, would map to say a 512 dimensional vector that represents the encoding for this edge. Shown here is a visual illustration of what these graphs look like. In this case, we're looking at a binary graph where we only have one kind of relation between nodes. For example, this relation could denote are friends. So for example, 6 and 7 are friends, 6 and 5 are friends, 1 and 2 are friends, but 1 is not friends with 7 or 6. This is the kind of information we can communicate with this graph structured data. And graph structured data is very natural to data domains, application domains like social media, road networks, knowledge graphs, chemical molecules, protein-protein interactions, all sorts of these ideas. There are all sorts of examples. The application domains in this field of graph structured data is constantly growing and exploding with interest. So now that we've done the basic overview of what graph structured data is, we'll begin talking about how we can convert nodes in graphs into vector representations by using two general different paradigms for constructing and optimizing these vector representations. So we'll start off with the difference between word2vec and BERT. Word2vec maximizes the similarity between two high-dimensional vectors by using some differentiable function, but not several layers of deep neural network processing. So BERT uses, say, 20 layers of sequential multi-head self-attention to finally end up with some vector representation for each of the two tokens, compared to just using one layer of differentiable computation or just taking the embeddings themselves and using some kind of optimization strategy to turn them into semantic vectors, compared to indexing what they call the penultimate layer of one of these neural networks to extract the vector representation for the high-dimensional data. In this vector search engine demo from Weaviate of the Wikidata graph dataset, we're going to be using graph embeddings from the PyTorch Big Graph framework. In this case, we're using the word-to-vec style of having direct embeddings for each source node, destination node, and an embedding for the relation. So we have several different relations in this Wikidata graph, and we have separate vector representations for each of these vectors, and we relate these source and destination vector embeddings by using these different kinds of functions. So we could have cosine distance, we could have just the dot product, we could have all these different kinds of ideas for computing the similarity between these two vectors. So generally we use cosine distance or L2 distance, these kinds of ideas to compare the distance between two of these continuous vectors with one another. Facebook AI Research developed an algorithmic framework to compute these graph embeddings for large-scale graphs in the PyTorch Big Graph framework. Facebook AI Research has open sourced these graph embeddings, and these are the graph embeddings that are used in the Weaviate vector search engine to search through Wikidata. Facebook's PyTorch Big Graph presents several interesting academic ideas if you're interested in this research and trying to figure out how to improve the state of embedding graphs at large scales. The first of which is block decomposition of the adjacency matrix. This decomposes these very large adjacency matrices so you can parallelize the training of the graph embeddings on a massive distributed computer, which also comes with a novel distributed execution model, which is how you do things like parameter locking and all sorts of communicating issues with having these large-scale distributed training systems. The next of which is efficient negative sampling. This is a strategy for negative sampling within batches in order to use contrastive learning. So when you're comparing the vector embeddings of source and destination nodes, you have negative destination nodes to further normalize this kind of optimization task. And then finally, we have per relation configuration options, which are related to setting up the block decomposition and all these kinds of ideas in the PyTorch Big Graph paper. If you're interested in this research, I highly recommend checking out this research paper. So now that we have a basic sense of what graph structure data is, how it's represented as continuous vector representations, and kind of the optimization tools like Facebook's PyTorch Big Graph that we're using in order to get these node embeddings for nodes in a large-scale knowledge graph. So here's an example of the San Francisco node encoding in the Wikidata graph, examples of different properties it has, edges, relations, with other nodes that are contained in this Wikidata knowledge graph. So we have 90 million different node embeddings that are computed and uploaded into this Weaviate vector search demo, and they're related to each other based on these different kinds of relations. So in PyTorch Big Graph, they're optimizing the similarity of these nodes based on the vector embeddings for each of these relations as well. So it's a very interesting optimization problem, and now we get to see what this finally looks like with a web demo provided by Weaviate. Shown on screen is the Weaviate vector search engine demo for the Wikidata dataset. We also have the Weaviate console view, which is how we view most of the datasets in Weaviate, and a great way to test the GraphQL search functionality for semantic vector search. But in this case, it makes more sense and is a better visualization to look through the images to visualize the nearest neighbors in this kind of Wikidata style of representation. But in the future, we'll also be looking at web demos that are hosted in the semi-console with respect to using this GraphQL interface for your vector search, and then having the output come in this kind of format. So here is the vector search demo. In Wikidata, we have these Q numbers that represent these different kinds of entities. So for example, food, just the word food in the entry for food in Wikidata is represented as Q 2095. So we type in the Wikidata encoding for the node, and then we hit search to search through nearest neighbors. So interestingly, we find that we don't always get great results. If we put in wine, which is Q282, maybe we'll see a better example. But in general, we don't get the best results for nearest nodes with these current Wikidata embeddings. But thanks to the Weaviate console, we can now study this better and make more progress in the research direction towards making graph embeddings work well for finding nearest neighbors. So here's another example of putting in the Wikidata embedding for television. We see that we find other kinds of entertainment categories, but generally it's still a work in progress in making this work for every node in the Wikidata graph. As mentioned earlier in the video, one theoretical advantage of graph structured data compared to raw text representations might be that it's better at representing new entities or specific entities that describe brand names and things like that in the real world. Another example might be that it's easier to update the information in this kind of graph structured representation. So for example, if the Miami Heat are suddenly kicked out of the NBA, we could just delete this edge compared to having to delete all the text in Wikipedia that might reference the Miami Heat as currently being an NBA team. So as a final example to inspire your interest in checking out the Weaviate demo for the Wikidata embeddings, here's the graph search with the deep learning node. As we search for deep learning, we see that we find nearest node neighbors like deep neural network, convolutional neural network, machine learning, and feed-forward network. So these are kind of interesting results for searching for the deep learning node. And what would be really exciting is to see these kind of specific categories of deep learning research topics become usable for semantic nearest neighbor search. So say you type in weak supervision and you find label propagation, semi-supervised learning, using this kind of tool for knowledge discovery for deep learning research scientists would be a really great first application for seeing more and more research and applications get developed around this kind of idea. Knowledge graphs are one example of how we can use graph embeddings in frameworks like PyTorch Big Graph, or these kind of graph embedding schemes like the complex strategy of aligning these embeddings. There are many other interesting examples of graph structured data, and here are some of the examples that I'm personally very interested in. The first of which is drug repurposing, with these kind of knowledge graphs that describe particular characteristics of drugs and the kind of things that they look for when they're developing and testing novel drugs. So for example, they look at if it inhibits this kind of biological pathway, promotes some kind of other metabolic process, or if it binds to some kind of receptor protein in a virus, these kinds of ideas. I'm not a biologist or any kind of background on that, but I have read these, like a basic sense of this to produce this paper, Deep Learning Applications for COVID-19. So when I was doing this research, I came across these knowledge graphs, and I thought that this was the key application that finally, to me at least, sold this idea of knowledge graphs and why this is such an important technology. So I highly recommend checking out these drug repurposing knowledge graphs. As mentioned in this paper cited in the image, the Benevolent AI Knowledge Graph is a really great place to start, and I think Stanford University on their YouTube channel has also published a week of lectures around knowledge graphs. So these are some really great examples, and particularly motivated around this idea of trying to find some new drug like this baricitinib drug that would help treat COVID-19 by looking through similar kinds of pathways as they extract and particularly label these relations that are important for developing drugs. I'm also really excited about scientific literature mining applications with natural language processing and all sorts of other domains, as we're seeing graph neural networks and graph structure data also be a very exciting domain for knowledge discovery and scientific literature mining. I highly recommend checking out this example in Keras Code Examples, classified as one of the graph data Keras Code Examples. This shows you how to use a graph neural network to predict the subject of a paper given its citations as well as an initial feature representation of the words in the paper. So I'm not sure, so we have these examples of these graphs with citations. So for example, the MoCo version 2 paper probably cites SimClear and some other paper on contrastive learning if you're familiar with this kind of body of research. Similarly, Roberta probably cites BERT, and it probably cites GPT-2 or the original Attention is All You Need paper. These kind of citation graphs emerge in the discovery of these things, and this kind of graph structured information could be a very useful tool for searching through the scientific literature. So for example, we always want to try to find a similar kind of paper as we're writing and publishing these deep learning papers. I would personally be extremely interested in seeing if I could find a paper that has nearly the exact same idea as what I've written about in one of these papers that I'm working on for my PhD, and generally as scientists out there, and the point of this YouTube channel is to cover these kinds of papers. But it'd be really exciting if you had this kind of graph embedding and then did some kind of vector nearest neighbor search, like what's being communicated with Weaviate in this video, to find a paper that's identical to yours or very close to yours. And I think this is a very exciting and powerful idea. The project that I'm currently investing most of my time and energy into right now is Keras-BERT. Keras-BERT is a language model trained on this incredible data set of the Keras Code Examples. Community contributors have been adding these really exciting cutting-edge research ideas implemented in Keras to this repository of Keras Code Examples. This code example repository is linked in the description of this video, and I highly recommend checking this out to get information about how to implement these ideas and start doing deep learning research of your own. So Keras-BERT is a language model that's trained on the raw text of these kinds of Keras code examples, both the natural language descriptions as well as the code, and problematically also the code output as well. So there's all sorts of decisions I still have to make with trying to figure out how to make this kind of language model work, how to improve on the search through the Keras documentation by using deep neural network models and vector search engines like the Weaviate vector search engine. I'm looking to improve the Keras-BERT language model by adding graph-structured information to the dataset. So for example, we might have a bipartite graph where we have user item is a frequent kind of bipartite graph you'll see in these applications like e-commerce platforms. And in this case, on one end of the bipartite graph, we have the Keras code examples, and then on the right side, we have the Keras API and different components of the Keras deep learning framework. So for example, the Keras code examples, image classification from scratch, and compact convolutional transformers both use the two-dimensional convolution layer. Similarly, compact convolution transformers and text classification from scratch both use the embedding layer from the Keras layers classes. So this is one example of trying to add some graph structured data into this and trying to use techniques like the PyTorch Big Graph thing to have node embeddings. But naturally, this is going to require really scaling up the number of nodes and getting creative with the different kinds of ways that we source them, as well as the different kind of edge types in order to create something of the scale of Wikidata and start trying to apply this to the application domain that I'm personally the most excited about. I want to end this video introducing the Wikidata Weaviate demo with some of my general thoughts around knowledge graphs and deep learning with graph structured data, and generally how my thinking about this has grown. So first of which, with PyTorch Big Graph, I think this is an enormous step towards solving the problem of scaling up knowledge graphs to large-scale graphs like Wikidata, and then open sourcing them and putting them into open vector search engine demos lets researchers and scientists out there to see what this really looks like and see how well this kind of algorithm really works. So generally, I'm very excited about the research that Michael Bronstein is doing, things like geometric deep learning, algebraic topology, all these exciting ideas, and generally this field of graph neural networks definitely seems like something to bet on. So then I'm really excited about Weaviate. It's a really easy interface to combine text and graph structured data. So it's really easy to dump in these articles or different kinds of text data that you might have and then connect them to high-level objects by using these cross-references in Weaviate. And I'm going to be doing a full tutorial on showing how I've imported Keras-BERT into Weaviate. And I think once you watch this, you'll be really excited about the platform that Weaviate provides to integrate this kind of science and the product of semantic search and allow us to explore these ideas of knowledge graphs and what kind of advantages we have with the embeddings they produce. Generally, I think the flexible interface of graph construction is very exciting. You can have multiple node types, like for example, when we had the bipartite graph and we had the Keras code examples and then the Keras API, you can construct all sorts of different nodes in these kinds of knowledge graphs. You can also have labels for the nodes, like the citation graphs, where they have labels like computer vision, natural language processing, graph structured data, or maybe more fine-grained things like weak supervision, semi-supervised learning, active learning, these kinds of ideas. And then you can also have multiple relations. So it's a very flexible kind of way of representing data, and it might be the most flexible interface for posing learning tasks. And that's kind of how I think of it as a way of labeling data, more so than I think of it as data that is naturally graph structured, like chemical molecules, social networks, road networks, these kinds of things that are naturally graph structured. I think there's a difference between, say, knowledge graphs where they're not maybe most natively represented as graphs, but adding this kind of graph structured labeling really facilitates deep learning based optimization techniques. To summarize, my current thinking on graphs and deep learning is that it's more analogous to data labeling rather than an inherent data type. I definitely think the domains where it's an inherent data type, like predicting chemical properties of molecules and predicting travel times on road networks like DeepMind's estimated travel arrival time, these kind of things by using naturally graph structured data. But I think in domains like images, text, and audio that we're kind of studying the most, I'd say, it's more of a data labeling idea and an idea of how to use more labels. But I don't see it as being the same thing as neural structured learning. Neural structured learning is where you're applying the graph labeling right at the output layer, so right at the supervision layer, and it's more of a way of guiding the loss function and the computing of the loss rather than it is about some kind of thing that's put into the intermediate processing of these sequentially processing deep neural network systems. So you want it to be something that's fused with the information at layers 1, 2, 3, 4, as it builds up this representation and integrates the graph structured information. So I expect this to be very interesting for multimodal learning. You can already think about, say, image classification as being a bipartite mapping between raw pixel images and then natural language class labels of things like dog, deer, ship, and then as you get more descriptive, with describing the different kinds of classes. So overall, that summarizes how I'm currently thinking about graphs and how this kind of thing can advance the state of deep learning. If you're curious about graphs and deep learning, I highly recommend reading this PhD dissertation from Thomas Kipf, Deep Learning with Graph Structured Representations. This is a really great really like a book. It's something around 200 pages that outlines a lot of very exciting ideas for using graph structured representations in deep learning, things like graph convolutional networks, this slot attention thing, all these kinds of ideas around using graph structured data and how that integrates with most of these current deep learning workflows. So that concludes this explanation of the Wikidata Weaviate vector search engine demo. I'm really excited about bringing these vector search engine demos, making them openly accessible, and anyone can just do one click and then perform vector searches. So also available is the Weaviate demo with Wikipedia, and there's going to be a Henry AI Labs video coming very soon that explains Wikipedia and all these ideas behind neural search with Wikipedia, which is just the raw text representation compared to these graph structured representations. So I'm really excited about this video, and please stay tuned for it coming very soon. Thank you so much for watching this video. Please check out the Wikidata Weaviate demo for yourself, and please subscribe to Henry AI Labs for more deep learning and AI videos.